Hello, everyone, and welcome to lab number 11, which is experiment number 7, a gas law simulation. So in this experiment, you will be using a simulated gas chamber to verify the gas laws, such as the ideal gas law, PV equals nRT, and then the more specific gas laws, such as Boyle's law, Charles's law, and Avogadro's law, as well as Guy-Lussac's law. And to perform various gas law related calculations, such as to calculate the universal gas constant, which we use the capital R, and we will do that using a root mean squared equation. So just to, by way of introduction, the ideal gas law is PV equals nRT, where P stands for pressure, which is the force exerted by a gas against the walls of a container. There are multiple units of measurement that can be used for pressure, such as atmosphere, millimeters of mercury, torr, or pascals. And then there's capital V for volume, which is the space occupied by the gas. Volume is typically measured in either liters or milliliters. Capital T for temperature. Temperature is the determining factor of the kinetic energy of gas particles, right? So as you increase the temperature, gas particles have more kinetic energy. Temperature is typically measured in degrees Celsius or Kelvin. It could also be Fahrenheit, but not as commonly. And it is important to note that Kelvin is required in gas law calculations. So if you're given degrees Celsius, you do have to convert that to the temperature in Kelvin. And then little n stands for the amount of the gas, and that is the quantity of the gas present in the container. Quantities could be measured in grams or more commonly moles, and moles is required in the calculations. And then you also see the capital R, that is the universal gas constant, and the value of it depends on the units. The two most common values are shown over here to the right. 0.0821 liters times atmospheres over moles times Kelvin, or 8.314 joules over moles times Kelvin. And we'll be seeing both of those in this experiment. I included a table here from your book about conversion factors for pressure. So if you are using pressure in an equation, you don't have to convert to a certain unit, as long as you're either solving for the pressure in the unit that you want, right? Or a unit that you can convert to after you solve the equation. And if it cancels out, it's also fine for it to be in any unit. But most commonly, we would be looking at atmospheres or millimeters of mercury. So let's, at this point, go ahead and take a look at the simulator, which is linked in the experiment, and I also linked it in the PowerPoint slides. So this is the simulator. It's a little bit difficult to use at first, so it would be good for you to just come over here and play around with changing some settings to see how this works. So first of all, down here is the lever where you can release all of the gas. So it's like opening up this piston and it releases all of the gas that's in there. If you want to add gas back in, you can do a certain number of pumps of gas, right? So you can click on this once, right, for one pump. If it asks you to do 2 pumps, right, you could click on it again. You can even do 3 pumps, right, or more. Notice that the little red balls are indicating that this is gas A, and there's also a gas B. Up here we have the volume, right? The volume can be in an unlocked state, so it could change given changes in the other variables, or if you don't want it to change, you can lock the volume. And it will tell you in the procedure whether or not to lock or unlock the volume. But if it's unlocked, right, we can change the volume. The problem is there's no way to just tell it to go to a certain number. Like if I had wanted 500 liters, right, I can kind of try to get there, and you see how I'm like clicking, right? But I just went right by it. So I can go back up, right? And it's kind of very difficult to get exactly what you want. So you kind of have to play around with it. But a lot of times in the procedure, it'll say, you know, approximately 500. So you can use a different value as long as you mark it down in your table. That's not exactly 500 if it's too difficult to get to, you know, a certain value. All right, so we can lock that or keep that unlocked. And then we can also change the temperature by heating or cooling, right? So we can heat, right now it's 325 Kelvin, right? But this is just like the other one. It's sort of click and click, right? And trying to get it to whatever value you might want. And that's it. There's no way to directly change the pressure. The pressure is just read based on the other variables. So when we want a certain pressure, the procedure will tell you, for example, to like heat it up, right, to whatever temperature it takes to get a certain pressure. And I'll keep coming back here to show you, you know, how to set things up for each table. We won't use this until a little bit later in the experiment, right? But we can read the average kinetic energy in kilojoules per mole, or what's called the RMS, which is the root mean squared in meters per second. So, and again, we will come back to that. For now, let's go back to the PowerPoint slides. All right, so let's talk about the procedure and some general information that it's good to know before we get started. First, we're going to investigate the relationships between the 4 gas variables. So variables are things that are not constant, right? So R, which is a constant, is not considered a variable. So the variables are volume, pressure, temperature in Kelvin, and the number of particles in moles, right? So there's 6 different combinations that we are going to explore. We're going to explore what is the volume temperature relationship. Meaning, for example, if I change the temperature, right, how will the volume change given everything else remains constant? We can also look at volume pressure relationships, temperature pressure, volume moles, moles pressure, and temperature and moles. For each of these combinations, if we want to see the effect of changing one on the other, then we must keep the other 2 variables constant. So for example, when we are looking at volume temperature relationship, we're going to make sure to keep the number of moles and the pressure constant. And prior to each new data table, we're going to empty the chamber by opening the valve. Then the first data point is actually given in each table, and we will need to collect data to complete the rest of the table. We're going to select gas A, which is what is selected by default for parts 1 through 7A. And then for table 7B, we'll switch to gas B. All right, let's look at table 1, which is investigating volume and pressure. So the instructions are here for exactly what to do, right? And we'll go through that as we go back to the simulator in just a moment. And then notice that they gave us the pressure reading, right, for the first set of data. So that is for us, and we're going to be keeping temperature and moles constant in this table, right, and then filling in the data for the rest of the table. So let's go ahead and take a look at how we do that. We'll go back to the simulator. And I'm going to read off the instructions and follow the instructions so you can see what I'm doing. So it says empty the gas chamber before you start. So let's go ahead and empty that. It's going to take multiple clicks on that red lever to completely empty the gas because I had put multiple pumps of gas in there before. Okay, and now it says adjust the temperature to 295 Kelvin or somewhere within 5 Kelvin. Because remember how difficult it is to exactly get, 295. I really got lucky on that one, so I'll leave it. But if I had 290 or 300, that's fine. And then I would just want to make a note in the table that instead of doing it at 295, right, I did it at like 300 or 290. But, don't drive yourself crazy trying to get the exact number. Pump the plunger once and then adjust the volume to a range between 300 and 400 liters. So pump the plunger, and it says adjust the volume to 300 to 400 liters. So again, we can kind of be in that range, right? Anywhere you want to be in this range is totally fine. Okay, so we have 396 liters. So I would go ahead and put that in my table. So right where it says 300 to 400 liters, and there's a little line next to it, we'll write 396 liters. And then we're going to write down the pressure, which is 1.83 atmospheres. Which I'm finding really weird just because it says it's supposed to be anywhere from 2.67 to 2.00. Okay. Let's see. Maybe we can come down here, see what it would be if I change it a little bit. So now it's sort of in the range. So 300 to 400 liters. Say it was 366. Wow. Well, we're just going to write down whatever it says, even though it doesn't seem to be in his range here for this one. Okay, so whatever you do, right, we're just going to be adjusting and writing down what we see, okay? So at 366 liters, it was 1.98 atmospheres. Now it wants you to keep the previous temperature and the number of particles the same. So remember, whatever we did, 295, we'll just keep it the same. Don't do any more clicks, same number of particles. Adjust the volume to a range between 500 and 600 liters. So somewhere in that range, you can write down 556 liters and then 1.31 atmospheres. Right, and then lastly, we'll adjust to somewhere between 800 and 900. Right, like 866, and then write down 0.84 atmospheres. So you get the idea. We have to follow the instructions, right? Do the best we can. Don't get too bogged down if you don't get the exact values that were in the table. So going back to this, right? I happened to get lucky at 295 Kelvin. But if I was reading at 300, for example, I would just change all of this to 300, right? I would write the exact volume that I had. Remember, I was just trying to hit this range, and then write the exact pressure, right, associated with that. And don't forget to take a screenshot, right, of the gas simulator for using the last volume range. All right, so for table 2, we're investigating the volume temperature relationship. So we're going to go back to the simulator. Remember, we always want to empty the chamber, right, when we're moving on to the next table. All right, so it says make sure to have the volume unlocked. Pump the plunger once, which will adjust the pressure. Right now we're at 1 atmosphere. Next, set the temperature between 75 and 100 Kelvin. We're going to cool this way down. So we're at 100 Kelvin. That will adjust the volume, right? And we're just going to write that down. We're exactly at 100 Kelvin, right? And our volume is 246 liters. And then you're going to adjust the temperature to between 125 and 150 and read the volume. Lastly, adjust to between 175 and 200 Kelvin and then read the volume. Right, so again, we just want to fill out the table, write down whatever temperature you used in this range, and then what the volume was. Then you can move on to table 3, where we're going to be looking at the relationship between the volume and the amount or the number of moles of gas in the chamber. So let's go back to the simulator. Remember, we're always going to empty the chamber. And then we are going to adjust the temperature to 70 Kelvin or thereabouts, it says. So again, we're not going to set, I always somehow get lucky, but when I was doing it before, I was not getting so lucky. So I'm at 70 Kelvin again. If approximately, if you're, slightly different, just record that under the temperature that you weren't at 70, but instead like 65 Kelvin or something like that. Pump the plunger once, it says, right? And it will adjust the volume and pressure accordingly. Record the number of pumps and the volume in the table below. So we had 1 pump, and we're going to record our volume, right? And we can do that for 2 pumps and 3 pumps, right? So make sure you start by keeping the previous pressure and the number of particles the same as the last setting. Keep the volume setting unlocked. Pump the plunger a second time. Let's go ahead and try that, right? So notice that the pressure, right, stayed the same. And the temperature stayed the same. So those are the 2 ones that are going to remain constant here, is constant pressure, constant temperature. We doubled the number of moles of gas, right? And so our volume goes up. And we're going to record that. And then if we add more gas in there, right, we'll record our volume here. So we've looked at the relationship between the number of moles of gas and how that will affect the volume, right, given a constant temperature and pressure. Make sure you're taking screenshots where it tells you to take screenshots. Table 4 is looking at the pressure-temperature relationship. So if we come back to the simulator, remember we're always going to empty the chamber first. And then it says adjust the temperature to 315 Kelvin or thereabouts, right? So we'll go up. So it's a little hard to get exactly 315, but we'll be happy with 320. So I would just go ahead and cross out 315 and write 320. And we're going to keep that temperature constant for table 5. It says add 1 pump of gas. So we'll go ahead and click on the plunger once. And then adjust the volume to 500 liters or thereabouts. We'll attempt to do our best. We're going to be happy with 497, right? And we'll go ahead and cross out 500 liters and write 497. That's pretty close. And it says to lock the volume setting for this one. Now the pressure will adjust accordingly, so we can record the pressure and the number of pumps in the table below. Right, so for we already put in one pump, so we want to write down the pressure here, and then we can keep adding in, right, a second pump, record the pressure, and a third pump, record the pressure. So that's what you needed to do for table 5. All right, let's go ahead and look and see what's the next table. So here we're looking at a pressure and number of moles relationship. And again, the instructions are all right there for exactly what to do, right? But we're going to come back to the simulator, always empty out all of the gas, right? It says add gas particles in the chamber by pumping once, and then adjust the volume to 500 liters approximately. And I can decide how much I want to play with that to get it pretty close. So I'm okay with 507 liters. So I would just cross out 500 liters in table 6 and write 507 liters. Right, and now it says adjust the, oh, we don't want to forget to lock the volume. Adjust the temperature such that the pressure changes to 1 atmosphere. Right, so if I cool this down, right, we can again attempt to get pretty close to 1 atmosphere. Don't be too worried if it's not exactly that, right? 0.97 atmospheres is fine. It says record the temperature and the number of pumps in the table, right? So we have 1 pump in there, so we'll record the temperature, right? And if we add another pump, then we're going to so we had 2 pumps, but now we need to again adjust the temperature to try to get to 1 atmospheres. Oops, went a little too far. See if I can get it a little closer. You can see it gets a little crazy. Because it really wants to not give me 1 atmosphere. Kind of see how close I can get. Well, that should be fine for now. So again, I'll just kind of write what the pressure was, did my best to get to 1 atmosphere, right? So we have 2 pumps in there, and we want to write down the temperature as well, right? And then again, same thing, we're going to add a 3rd pump, right? We're going to adjust the temperature to try to get as close as we can to 1 atmosphere and record that information in the table. All right, table 6 is looking at a temperature and number of moles. And for this one, we will, again, release all the gas. Add gas particles by pumping once, and then adjust the volume to 500 liters. Perfect. We locked it, adjust the temperature such that the pressure changes. Oh, I think I was doing that one before, this table. Anyway, okay, we're gonna move on. Somehow I might not have come back here and looked at this, but we were doing that one before. All right, we will move on in any case to table 7A, which we're going to be working on calculating the universal gas constant R using the root mean square equation. All right, so this is what the table looks like. And initially it looks a little like, okay, there's a lot going on, right? And we're not exactly sure what to do. But, right, we can just follow the instructions and record, right, pressure and root mean squared, which we saw was on the gas simulator. In this one, the volume is being held constant at 1,000 liters. We're going to vary the temperature and look at when there's 1 pump, 2 pumps, or 3 pumps in terms of the number of moles of gas A, what that does to the temperature. All right, so going back to the simulator, it says, make sure that you're using gas A, which we've always been using gas A, so there's no difference there. Empty the gas chamber, add gas particles by pumping once, and then adjust the temperature to 10 Kelvin. So luckily, that is the lowest temperature it goes, so it's very easy to get there. Increase the volume to 1,000 liters and lock. That, I believe, is also the largest volume it goes to. So just let it go all the way up and then hit lock. Complete the table below by recording the number of pumps, the temperature, volume, pressure, and the root mean squared. Right, so we are first just going to be looking at just 1 pump of gas, right? We're going to vary the temperature starting from 10 Kelvin, going up to 100 Kelvin, then 300 Kelvin. And as we increase the temperature, we're going to be recording the pressure and the root mean squared. So right now, under 10 Kelvin, we're going to write down the pressure that we see and the root mean squared in meters per second. So we'll record that in our table. Then we're going to go up to 100, or as close as we can get to that, right? You can, depending on how much time you want to spend trying to get to exactly 100, you can always change it, right, to instead of 195. We're going to write down the pressure, right, and then write down the root mean squared in the equation. So you get the idea. We're going to be completing that table. There's 5 different temperatures we're looking at with 1 pump. Then we'll increase to 2 pumps, look at 2 different temperatures, record pressure and the root mean squared. And then we'll do 3 pumps at 2 different temperatures. We'll record the pressure and the root mean squared. So that should be fairly straightforward. I'm sure you're getting used to the simulator by now, right? And make sure you're taking your screenshot as requested. All right, for table 7B, we are going to switch to gas B for this part. So that's going to be the main difference, right? So going back to the simulator, we're just going to switch to gas B. So to do that, you have to click on gas B and then unclick, right, on gas A. We'll just get rid of that. And then again, put in a pump of gas B. So this one, again, the volume is going to be constant at 1,000 liters. So we'll just go ahead and lock that. And then we're going to be looking at a variety of temperatures, starting with 10 Kelvin. Notice how slow the molecules move at that low temperature. And we're going to record the pressure and the root mean squared, which is here under B, right? And then we're going to increase to approximately 100 Kelvin, then 300 Kelvin, then 600 Kelvin, record the change in temperature and the change in the kinetic energy, which is the root mean squared. And we'll talk about that in a little bit. All right, so at this point, you should be through collecting the data in the data tables. There is a data sheet where you just copy your data over in case you had done a lot of scribbling or something like that. You can make a nice clean copy to turn in. And then we can work our way to the calculation analysis section on page 102. And it starts with this table where we're going to look at all of our tables of data that we collected, right? 1 through 6, and all of the relationships between 2 variables we were looking at. And we're just going to write when we increased the first variable or decreased, right? What happened to the second variable? So for example, in the first table, right, when we increased the volume, what happened to the temperature? Did it increase or decrease? And you're going to go through and look at all of the tables and fill this out. And then don't forget that you should be able to look at the ideal gas law and check whether or not this makes sense, right? Because we have PV equals nRT. So if variables are on opposite sides of the equal sign, for example, pressure is on the left, right, and temperature is on the right, then they should be directly proportional, meaning as one goes up, the other goes up, or as one goes down, the other goes down. Excuse me. But if the variables are on the same side of the equation, for example, pressure and volume, because we have PV equals, right? So P and V are on the same side of the equal sign, then they'll be inversely proportional, meaning as one goes up, it causes the other to decrease, right? So we can look at the data in our tables and then later check to make sure that that matches what our expectation was given our understanding of the ideal gas law. And then this wants us to come up with some equations where instead of an equal sign, there is a symbol that means proportional to. It's not equal to because we don't have the constant, right, which is evening out the sides. But proportional to just means we can state relationship. So as one goes up, the other goes up, or as one goes up, the other proportionately goes down, right? So we want to, in all four of these, right, equations, we want to have just one variable on the left, and then the other three variables on the right, right? So all of these equations will have the P, the V, the N, and the T. And if they're directly proportional, then they'll both be in the numerator, right? So whatever pressure is directly proportional to will be in the numerator. And anything that it's inversely proportional to will go in the denominator, right? And you can also think about what it should look like given the ideal gas law equation. Because remember, we're basically solving for each of these variables, right? And you solve this equation for a variable, like for example, we can solve for P by dividing each side of the equation by V. V would cancel on the left, and it would be in the denominator on the right then. So we can say that the pressure should be directly proportional to the number of moles and the temperature, and then inversely proportional to the volume. So we're basically solving these equations, but because there's no R there, right, we don't have an equal sign, but just a proportional symbol. And we'll have the other three variables in the equation. All right, next we're going to be calculating the universal gas constant using the root mean squared equation. And so this looks really complicated, and so I've attempted to break this down for you so that you can fill in the data table on page 103. So first of all, we're going to be using this root mean squared equation. And based on kinetic molecular theory, the average speed of a gas is directly proportional to the absolute temperature. So notice that U, RMS, that's talking about the average speed of the gas. It's directly proportional, right, to the temperature. Of course, there's other factors here, right, that we have the square root, 3 times R times T, but just looking at the variables, because they're both in the numerator, right, it's directly proportional to the absolute temperature, and then inversely proportional to the molar mass of the gas. So rearranging this equation for R, we have R is equal to the molar mass times the root mean squared value squared divided by 3 times the temperature. And they've just called it R prime just because we are going to be looking at R using 2 different sets of variables. R prime, the units will be in sorry, not 2 different sets of variables, 2 different sets of units. R prime will be in joules divided by moles times Kelvin, and R double prime will be in units of liters times atmospheres, right, over moles times Kelvin. So this conversion factor just helps us convert the joules that was in the numerator up here to liters times atmospheres in the numerator. And then we're still over moles times Kelvin because it's the same equation from here to here. Okay, so these are our two equations, and this is just an example calculation using those equations. So in the example calculation, they used a different molar mass, right? It says the molar mass is equal to 32.0 times 10 to the negative 3 kilograms per mole. But it tells you instead of this value, you're going to use 3.00 times 10 to the negative 3 kilograms per mole, and not the other molar mass that was used in the example calculation. So we'll just move this value in here, right, which is the molar mass, right, capital M. And then notice the next part of the equation is the root mean squared, right? And so we're going to take that value, we recorded that in our data table, right? So we'll be able to get this from the data table, and we're going to be squaring that value. And then we're going to divide by 3 times the temperature. Remember that the temperature must be in Kelvin, but luckily it was already recorded in Kelvin in your data table. So we're going to get the temperature, right, from the data table and place it into this equation as well. The value we get will be in joules over moles times Kelvin. For our double prime, we're just going to be taking that value and dividing it by 101.3 joules, such that our number now will be in different units. It will be in liters times atmospheres over moles times Kelvin. Right, so we're going to be filling out this table, and you can actually look at, let's see, I believe it was the 7A, right? Table 7A from before. And we can actually just copy this information from that previous table, right? Remember when we looked at the number of pumps, right? The different temperatures, we recorded pressure and we recorded the root mean square value. So we can just copy that data, right, from our previous data table, which was data table 7A. And then we're going to be doing calculations of R prime and R double prime, right? I just talked about how to do those calculations. We're going to be using these equations, right, in order to get the value in 2 different sets of units. And remember that this is always going to be the molar mass, and this will be, these 2 pieces of information will come from the data table, right? So temperature comes from the data table, root mean squared comes from the data table, and we're plugging that all in, right, to get these values. I'll just give you a clue. These values should be really close to the values that we saw on a previous slide, right? So you go back, way back here to the very beginning, right? I gave you the universal gas constant R with 2 different sets of units. So in liters times atmospheres over moles times Kelvin, this is like R double prime. And then in joules over moles times Kelvin, which is like R prime. So the values that you should be calculating should be pretty close to these values. So if you're getting a number pretty close to that, then you know you're doing the calculations correctly. And we'll go ahead and calculate the average down here. To do that, we sum up all of the values and then divide by the number of values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'd sum up all of these numbers and divide by 9 to get the average R value. All right, so for the next calculation, right, we need to record our average R prime value from the previous table right in here into the data table here. This is gas B, so we want to look at table 7B and copy the values for pressure, right, and root mean squared. And you can also change the temperature. If you weren't able to get exactly these temperatures, right, and you use something slightly similar, but slightly different, you could just write, instead of 100 Kelvin, for example, I use 95 Kelvin, because that's important because that goes into the calculation. So make sure that you're looking at table 7B and copying as much of that data into this table as you can. Right, this was previously calculated in the last one, and now we're going to be calculating the molar mass of gas B. In order to do that, we are going to use this equation for calculating molar mass, which was rearranged to solve for M in our previous root mean squared equation. So again, it's 3 times R. The R value, oops, I think I messed this up somehow. Sorry, this should be red and this should be purple. I'll try to fix that before I post the slides, right? Because down here, this is the root mean squared value, right? So that should be here, that should be the red box, right? And then this is your R prime value, which is the average value, right, from right here. And then we'll multiply by the temperature, which we can see is also given to us in the data table. Multiply that by 100, and you should get some amount in grams per mole. And you can just go ahead and, round that to the nearest whole number. And then it asks you about what is the identity of the gas given the molar mass of the gas. And so it's going to be a very simple gas. So look at the periodic table to figure out what diatomic gas or what simple gas might match that molar mass. All right, and then we're going to be calculating the number of moles, right, in each pump of gas. And so in order to calculate for the number of moles, we're going to rearrange the PV equals nRT equation to solve for N. So that means that N is equal to pressure times volume over the constant times temperature, right? And so we want to look back at data table 7A, and we can put in the pressure, right? The volume was constant. We'll use our average R, and then we will use the temperature, right? And we can use the one at 300 Kelvin, and then we can solve for the number of moles. So you'll want to do that for 1 pump, 2 pump, and 3 pumps, right? To see how many moles was coming over in every single pump. And it should be a multiple of the same number, right? So if there was 15 moles in the first pump, then in 2 pumps, there should be 30 moles, and in 3 pumps, there should be 45. That's not the correct answer, but I just wanted to give you an example. Okay, so let's look at the PreLab. So the PreLab questions start by saying a given amount of molecular oxygen gas is in a closed expandable container. So imagine like the simulated gas chamber. If the molecular oxygen acts as an ideal gas, answer the following questions. So what will happen to the volume if the temperature doubles and the pressure remains constant? Now, of course, you can look at the equation where volume and temperature are related, or you can just look at the ideal gas law to think about that. So it says it wants to know what will happen to the volume if the temperature doubles. So this value is going to double, and the pressure remains constant. And of course, the number of moles will also remain constant because it says some given amount of molecular oxygen gas is in a closed container. So no more gas is able to get in, no gas is able to get out. So it's going to be a constant volume, or sorry, a constant number of moles of gas. So what happens to the volume if pressure is constant and the temperature doubles? So that's a direct volume temperature relationship, or you can just say, okay, volume and temperature are directly proportional because they're on opposite sides of the equal sign. So if everything else is held constant, as temperature goes up, right, the volume should go up proportionally. What will happen if to the pressure if the volume is decreased by half and the temperature is doubled? So again, you can kind of imagine looking at the ideal gas law, and it says what will happen to the pressure, right? So you can think of an initial pressure, right? And then the volume is decreased by half and the temperature is doubled. So you can easily just kind of plug in values if it's hard to imagine changing two variables, like volume is changing and temperature is changing. So that makes it a little bit more complicated to think about theoretically. But if you were to like put in a value of, let's say, 2 for temperature and 2 for volume, right? We know that temperature is going to double, so 2 would go to 4, right? If the volume was 2 and it's decreased by half, it would go down to 1, right? So it would be 4 over 1, right? So you can think about what that would do, right? That would tell you how many times the pressure will increase. 4 over 1 is just 4, right? All right, the third question asks about a sample of molecular gas, the nitrogen gas, occupying 3 liters at a pressure of 3 atmospheres. So that's our initial volume, 3 liters, and our initial pressure is 3 atmospheres. And it says, what volume will it occupy when the pressure is changed to half an atmosphere and the temperature remains constant? So again, we can look at the ideal gas law, but at any time we can just sort of use one of the other laws that are just looking at 2 variables, right? There's an initial 2 variables and a final 2 variables. So in this case, everything else is being held constant except for the pressure and the volume, right? The pressure went from 3 atmospheres to half an atmosphere. So we know the initial pressure was 3 atmospheres and the final pressure was 0.5 atmospheres. We know the initial volume was 3 liters and we're trying to solve for the final volume. So solving for V2, we just divide each side of the equation by P2 and we get V2 equals P1 V1 over P2. So we can put in these variables. We don't need, having pressure in atmospheres is fine. It's going to cancel out and our volume will be given to us in liters. And then we have another case where now there's 3 variables that are changing, right? It says a 325 milliliter sample, so that's our initial volume of air at 0.95 atmospheres. So that's our initial pressure. And 30 degrees Celsius, that's our initial temperature. And it occupies what volume when the pressure changes? So this is now our final pressure of 1.05 atmospheres. And the temperature changes to 75 degrees Celsius. So that's our final temperature, or T2. Remember that we do have to convert the temperature to Kelvin, right? If this is given to us in degrees Celsius and it has to be converted to Kelvin, so we just take the temperature in degrees Celsius and add 273.15, and that will give us the temperature in Kelvin. So once we've changed both T1 and T2 into Kelvin, we're ready to plug values into an equation. There was a lot going on here. There was an initial pressure, initial volume, and initial temperature. It gave us the final pressure and the final temperature, and we're solving for the final volume. So we rearrange this equation to solve for V2. I did that by cross multiplying and then dividing each side by T1, P2 in order to get this equation. We can plug everything in after we've converted the temperatures to Kelvin to solve for the final volume. And then the last question says, molecular hydrogen gas was collected over water in a eudometer at 25 degrees Celsius when the atmospheric pressure was read as 752 millimeters of mercury. What was the pressure of molecular hydrogen gas? So this is just found by the equation that the total pressure will be the sum of the individual pressures of the different gases. So we have the pressure of hydrogen gas and the pressure of water. It tells us the total pressure, right, which was the 752 millimeters of mercury. And it tells us what the pressure of water is, right, at the same temperature. So we can just rearrange this equation to solve for the pressure of just the hydrogen gas. Looking at the post-lab, right, we have some more questions about what happens to the pressure if the gas volume is cut in half while N and T are held constant. So this is a relationship between pressure and volume, right? And moles and the temperature are held constant. So we can just use P1V1 equals P2V2. So it says what happens to the pressure, right? Or what will be the change from P1 to P2 when the volume is cut in half, right? So whatever volume is initial, let's say it's 20, it's cut in half to, let's say, 10, right? What will then happen to the pressure? Let's say the pressure was 10, right? What is it going to be once the volume is cut in half? So remember that these two numbers multiplied have to be equal, right? So you can also think pressure and volume are inversely related. So as one goes up, the other goes down, right? Proportionally. So if one doubles, the other one is cut in half, or vice versa. The second question is, what happens to the pressure if the gas temperature is increased while the number of moles in the volume are held constant? Again, we can look at the equation which relates pressure and temperature. So the initial pressure divided by the initial temperature is equal to the final pressure divided by the final temperature. And it wants to know what happens to the pressure if the gas temperature is increased, right? So T1 is increasing to some new value, T2. What is going to happen, right, to the pressure? And if it's hard to imagine that because these are in the denominator, sort of just imagine that these two have to be equal to each other. And you can put values in, right? So if the temperature is increased, maybe it goes from 1 to 2 or 1 to 5 or whatever it may be, right? What would happen to the pressure to keep those values equal to each other? So you want to think about that. The next question is sort of a theoretical question, right? Using our volume temperature relationship in table 2, what temperature should the gas volume fall to 0 liters, or at what temperature? So this is not something that you can see directly using the simulator because we weren't able to ever get the volume to be 0 liters. But you can imagine, right, if it went down to 0 liters, right, what the temperature would be, right? So this is sort of a theoretical temperature. I don't want to say too much to give it away, but hopefully if you look at the data or go back to the simulator, you can make a guess on that one. Using the value of 0.0821 liters times atmospheres over moles times Kelvin for R, and the pressure in atmospheres from table 3, calculate the number of gas particles N in your 2-pump sample. So whenever we're calculating for N, we can just rearrange the ideal gas law to solve for N, right? And we're going to look at table 3 again to get the pressure. The volume, I believe, in table 3 was, I don't remember if it was held constant or not. I'd have to go back and look, right? It tells you what value to use for R, and you'll get also the temperature from the table, and you'll solve for N, right? to see how many moles of gas were in that 2-pump sample. And then same sort of question for number 5, using the same value for R, the pressure will now find from table 5. We're going to again calculate the number of gas particles in our 3-pump sample. So we'll see, right, in 2 pumps and 3 pumps, does it make sense, right? The number of moles, of course, should be increasing by some constant value. All right, hopefully that helped. That was a little bit challenging to try to describe in a video. But as always, come and see me in office hours if you have any questions.